Okay, we've been talking chapter 9, I think, and that's stoichiometry. And last time we got into another type of stoichiometry problem, which is limiting reagent type of problems. And remember that the importance of the limiting reagent is it is the one that really determines how much product that you're going to make, because once it gets used up, which is essentially what the limiting reagent is the reactant that gets used up first in a chemical reaction. And once it gets used up, there's really no way to make any more products as a result of that. So when it is a limiting reagent problem, we want to figure out which one is the limiting reagent. As we talked about, there's two main ways you can kind of do that. More than two, really, but two that we talked about. The first way is you basically want to figure out how much, in this example, of B would be needed to use up all of A. So that's one way that you can figure it out. Just do a very simple sort of stoichiometry calculation between the two reactants, starting with one reactant where you use the starting amount of it, and you basically figure out how much of the other reactant you need, again, to completely use it up. If you have enough of that other reactant that you need, then that's the excess reagent. If you do not have enough, then that guy is going to be your limiting reagent. A reminder, if you're able to figure out one, the other is the other thing that's happening. So if you're able to figure out the limiting reagent, you also will be able to figure out which one is the excess reagent, kind of by default. The other very common way to do it as well is instead of doing it like that, you can just do two different calculations. And basically what you would do, for example, here, if we were interested in C, you would go from A to C and figure out how many grams of C you would produce if you started with A. And then you would do a separate calculation where you go from B to C and figure out how many grams of C you would produce if you started with B. And whichever one is the smallest number of grams would be both your limiting reagent and also your theoretical yield. So that's the other very common way of doing it. The way that you know it is a limiting reagent problem is you have enough information for your reactants that you could get the moles of each of those things. So that's kind of the key, that you know that it is a limiting reagent type situation. Again, they won't often in the problem tell you it's a limiting reagent problem, but that's really the thing that gets moles of both of those reactants based on the information given to you. Then you need to do that additional step, which, as we talked about, is through a calculation. It is not always the smallest number of moles of the reactants that's their limiting reagent. We also talked about percent yield, which is our actual divided by our theoretical times 100%. Actual and textbook problems are usually given to you, and that is the actual amount of product that you produce when you do the reaction. The theoretical is based on the equation and a calculation and how much you're starting with. And that could be just a basic stoichiometry problem, could be a limiting reagent type problem, but you would calculate that when you divide it to their higher percent yield is what we're looking for. Again, not over 100, because that, again, usually indicates that something went incorrect. Any questions on any of that stuff we talked about last time? All right, so I think we just have one more example to do here. So let us do it here. All right. So if you start with 100 grams of ammonia and 100 grams of carbon dioxide, and you produce 120 grams of our product here, what is the percent yield? So some numbers that might be helpful: nitrogen 1401, hydrogen 1.008, carbon 12.01, and oxygen perhaps 16. All right, so take a few moments there, work through the steps, and see what you come up with. We're looking for our percent yield, which is our actual equals divided by our theoretical times 100% yield. So again, in this problem, we do have our actual given to us, which is 120 grams. Again, the theoretical here, we do need to calculate. And once again here, what tells us this is a limiting reagent type situation is we have the grams of both reactants, which means we could get to the moles of both reactants. So again, that is the key thing to look for, to know that you do need to, again, do that limiting reagent calculation. So with that, it really doesn't matter sort of which way you choose. We do need to balance the equation, which it is. The next thing we really need to do is convert everybody into moles. So we'll do that first. We'll do NH3, which means we need the molar mass from the periodic table. So 1401 for the nitrogen, 3 times 1.008 for our hydrogens. Gonna give us there a little 1703, I think. 17.03 grams per mole. We'll also need the molar mass there of CO2. So that's going to be 12.01 for our carbon and 32 basically for our oxygens total. Going to give us 4401 grams per mole. So again, we're going to use that to convert into moles. And if we do that, we will start with our NH3. We'll take 100 grams of it, use the molar mass there to convert into moles. And that's going to get us 100 divided by 1703. Looks like a 5872, we'll call it. We'll convert our CO2 into moles, also 100 grams, divided by the molar mass here, 4401 grams per mole. 2.72. 2.2, I feel 72. There we go. Moles of CO2. So again, remember, this is your starting amounts of each of these things. So because it is a limiting reagent problem, I'm going to do the calculation to figure out which one is the limiting reagent. And in this case, I'm going to figure out how much CO2 is needed. So I'll start with my moles of NH3. I'm going to go to the equation, find the relationship between NH3 and CO2. And from the equation, we can see that for every 2 moles of NH3, which needs to go on the bottom here, we get 1 mole of CO2. And that means 5872 divided by 2, 2936 here is needed. So in this case, we need 2.936 moles of CO2. We are only starting with 2.271 moles of it. Do we have enough in this case? We do not have enough. So that means that this guy here would then be our limiting reagent, as we do not have enough of it. Any questions on that there? Once again, once we now know our limiting reagent, we could actually do the problem, which is to figure out how much of our product we're going to make. So we'll take our limiting reagent, 2.272 moles of CO2. We will now use the mole-to-mole relationship between our limiting reagent and our product, which from the equation is a 1-to-1 relationship. So 1 mole of CO2, 1 mole of our product here. That's going to give us 2.272 moles of our product. And we want grams since our actual yield's in grams. So we need the molar mass of our product. So that's going to be 2 times 1401 plus, it's like 4 times 1.008 plus 12.01 and 16. I think we used this earlier on. 6006 is the molar mass. We want the grams up on top. And that will get us here about 136.5 grams of our product in this case. Questions on that so far? That is obviously our theoretical yields, which would be the bottom part that we need. Now that we have both the actual and the theoretical, we can divide them out and get our percent yield. So we'll take the 120 that was given to us, we'll divide it by our 136.5, which is our theoretical we calculated, and that is going to get us a percent yield here of, if I punch in the right numbers, maybe better, about 87.91. Not terrible, pretty good. Percent yield. Any questions on that there? So again, as we talked about last time, one method here is basically the same steps that we do for our basic stoichiometry steps. Just between kind of the second and third step, you do your limiting reagent calculation, and then you continue on with the limiting reagent through the rest of it. Any questions on stoichiometry, limiting reagents? We also talked about excess reagents. Any questions? Okay, that wraps up this chapter, I believe. Okay, so the next chapter we're going to talk about, we're going to go ahead a little bit. Chapter 13, we're going to talk about gases, and we're going to talk about gas laws. So there's a number of gas laws in this chapter. So let's talk a little bit about gases and substances that exist as gases under normal conditions. So when we talk about sort of normal conditions, these are sort of like room temperature conditions, everyday sort of conditions. And that is usually refers to a pressure of 1 atmosphere, which is what an ATM stands for. And as we'll talk about, that's a very common unit of pressure, and a temperature of 25 degrees Celsius. So under these kind of normal conditions, we typically don't find ionic compounds in the gas phase. And that is because they are held together by that really strong electrostatic attraction between the positive ion and the negative ion that holds them together. On practice, you pretty much can only melt it. So you might remember maybe some of those early experiments where we had some like salt water, and you evaporate it off the water in your evaporating dish and stuff like that, and you're left with sort of a ionic compound there in the evaporating dish. You pretty much could heat the heck out of that ionic compound, and it will probably never go into the gas phase again. It will just really start to melt before it will jump into the gas phase, because that really, really strong attractive forces. Now, when we talk about molecular compounds or sort of covalent compounds, guys that are sharing electrons, they are a little bit different. There are certain molecular compounds like carbon monoxide, carbon dioxide, hydrogen chloride gas, ammonia, and methane, which are gases under normal conditions. But one of the major differences between a ionic compound and say a molecular compound in terms of gases and going into the gas phase is it is usually much, much easier to convert a molecular compound into a gas than it is an ionic compound. And that is because they are held together by intermolecular forces. So for example, if we had a couple of water molecules, which are polar as we know, oxygen being more negative, hydrogen side being more positive, and same thing here, there's an attractive force between the negative oxygen in one water, for example, and the positive hydrogen in another, which holds this entire water molecule together with this entire water molecule. That is what is known as hydrogen bonding. And that is what is referred to as a intermolecular force. And intermolecular forces are these forces that hold together basically two molecules, two same molecules, two different molecules. They're the forces that basically hold them together. And they are much weaker, for example, than any type of intramolecular force, which is essentially the force that holds together like an ionic compound, like the ionic bonding there between the positive ion and the negative ion. So when we have something like water, it's quite easy to convert into a gas because frankly, you just need to heat it. And when you heat it, the first thing that happens is we will break this bond between the water molecules. And speaking of intramolecular forces, if you look at just one water molecule, the covalent bonding between the oxygen and the hydrogen on both sides, that is what is known as an intramolecular force within a molecule. And again, those are always really stronger than any intermolecular forces. And we know that, for example, when you do heat up water, you get steam, right? When you make pasta. When you heat up water, you don't break these bonds. Because if you did, you get hydrogen and oxygen gas, which wouldn't be so great if you're trying to make pasta. So these guys are always stronger than these. So I just got to get to 100 degrees and off will go that gas molecule, off will go that gas molecule, our water molecule into the gas phase there. And you basically can separate it out. So typically speaking, the stronger the attractive force between a molecule like in itself, the less likely it would be held together. It would be less likely it'll be a gas under normal conditions because it'll be held together a lot stronger. That's why certain molecular guys, like for example methane, which is when you light your Bunsen burner and all that good stuff, um, and a lot of organic guys, which are nonpolar molecules, they're held together by dispersion forces. And dispersion forces are relatively weak intermolecular forces. They're very, very weak, and it doesn't take a lot for those guys to enter into the gas phase. So that's like a lot of organic guys like methane, propane, butane. Those are all gases under normal conditions, and it's because they're not held together very tightly, so they go into the gas phase. Also, like when you take organic later on in your chemistry career, they stick you in a fume hood because a lot of organic ones are nonpolar, which means a lot of reagents that you use are volatile, which means they could just pop into the gas phase pretty easily. Even if you just kind of open the bottle, they'll go kind of break apart. And even though they're sort of the liquid phase, they could go into the gas phase really, really easily. And you don't want to inhale all those things. So when we talk about gases under normal condition, it's our normal sort of guys: hydrogen, nitrogen, oxygen, fluorine, and chlorine. These guys are going to be gases. Ozone, which is O3, is also a gas. And then, of course, our noble gases are group 8 on the periodic table: helium, neon, argon, krypton, xenon, all the ons there. Those are, again, monoatomic gases. They come as ones. Remember, things like hydrogen, nitrogen, oxygen, fluorine, and chlorine comes as diatomic molecules, or they come as twos. So right there on the periodic table, pretty much to the left there with hydrogen, and then like all this area here are going to be gases under normal conditions. So when we talk about a gas, there is a difference when we talk about something that is a gas and really something that is a vapor. A gas is a substance that under normal conditions will be found in the gas phase. A vapor, on the other hand, is something that is normally found in the solid or liquid state, but can be converted into a gas. And that is why we oftentimes will refer to water as water vapor rather than water gas, because it just sounds funny, I suppose. But water vapor, because obviously water is normally found in the liquid state, but can be converted into a gas. So when we talk about gases, one of the most often sort of measurement of a gas is pressure. So we always sort of associate pressure with gases. And when we are in the gas phase, obviously, we're at the part where everybody is basically broken apart from each other, right? They're flying around with a lot of energy. And obviously, as they are flying around, they're going to start hitting the walls of the container, and there's going to be a lot of collisions. And the collisions that we have with gases is directly related to the pressure we associate with them. The more collisions that there are, the higher the pressure will be. Kind of the less collisions that you have, the lower the pressure will typically be. So the number of collisions and things that affect the number of collisions plays a big role in terms of the pressure that we associate with gases. And when we talk about pressure of gases, one of the ways that we measure pressure is through a barometer. And a barometer is, well, not anymore in a lot of places, but a classic barometer is a bucket there. I won't say a bucket, but a thing of mercury and a glass tube that's inside it. And as the atmospheric pressure sort of comes down on the mercury in the tube will start to actually rise. And mercury is an unusual sort of substance. It actually will have a reverse meniscus. It'll actually go upwards rather than downwards. And that is because the attractive forces between mercury in itself is greater than the attractive forces between mercury and the glass. So instead of going up like a traditional meniscus in the U shape, it actually comes in on itself and will come down. And if you ever come across a mercury barometer, which probably won't happen because most schools take them out of the labs, you usually actually read from the top of the meniscus because it actually goes the other way than what we traditionally see, which is that for a meniscus, where we read from the bottom. Now, when we talk about pressure, there's several different units of pressure, but I would say this is the big three in terms of units. We have an ATM, which is an atmosphere. We have a torr, which I'm assuming is named after the guy who invented the thermometer, maybe not the thermometer, the barometer, which is the torr, and one mmHg, which is millimeters of mercury. And that unit is because of a barometer had mercury in it. And typically on a barometer, there's frankly a ruler, and you could read the level of the mercury in the barometer in a lot of times inches of mercury, centimeters of mercury, and millimeters of mercury, which is again a common sort of unit. So 1 torr and 1 millimeter of mercury are equivalent to each other in terms of a one-to-one relationship. The relationship between atmospheres, millimeters of mercury, and torr is that 760 number. So if you have atmospheres and you want either millimeters of mercury or torr, you're going to multiply by 760, and that will get you millimeters of mercury or torr. And obviously opposite there, if you're starting with millimeters of mercury or torr, you're going to divide by 760 to get it to an atmosphere. So obviously those conversions you do need to know, right? So make sure that you know how to do those conversions. Those three, again, I would say are the big three in terms of pressure units. There are other units of pressure, things like PSI, which is pounds per square inch, pascals and kilopascals are also very common units of pressure, and a bar, which is like 1.01 atmospheres, is also another common unit. But I would say out of all those in your chemistry classes, these are probably going to be the big three in terms of units associated with pressure that you see there. Here is a nicer picture of a barometer. And again, most schools took them out years ago because they had mercury in it. We have a digital one, I think, in the lab. We also have one that's hanging up on the wall there by the oven, and it's not a mercury one. I think is alcohol-based barometer. As I mentioned before, here are a few other common units that you sometimes come across. Pascal or kilopascal. So 101,000 pascals basically is an atmosphere, 101.3 kilopascals, and our pounds per square inch, 14.7 psi in an atmosphere, and 1.01 bar is equal to 1 atmosphere. So these are some other units, but probably won't come across them too much, but you should probably still be aware of these other sort of units as well. So let's talk a little bit about gas laws here. And when we talk about gas laws, there's really three variables that we oftentimes will look at: pressure, volume, and temperature. So those are kind of the big three variables that we see with gas laws. So the first gas law we're going to look at is what is known as Boyle's law. And Boyle looked at the relationship between volume and pressure. So he looked at the relationship between volume and pressure, keeping temperature constant in this case. And what he found was that when you looked at the relationship between volume and pressure, the relationship is basically an opposite relationship. So what I mean by that is if you have a really small volume, that means that your gas molecules are going to be in a very, very small place, which most likely will mean you're going to have a lot more collisions is going to happen, right? Because they frankly just don't have a lot of place to fly around in. And because we're going to see an increase in the number of collisions because they're all hanging out in a closet, basically, and there's not a lot of room, we're going to see a dramatic increase in the pressure. So what he found was as the volume decreased, it's going to cause a lot more collisions, and we will see an increase in the pressure. Now, opposite of that is if we give everybody a little bit more room to kind of move around in and fly around in, now we're going to have our gas molecules in here, and it's going to take a little bit longer for things to collide with each other because they have a little bit more space. And what we're going to see is actually the number of collisions start to go down because there's a lot more room for everybody to fly around in. And as the volume goes up, the collisions go down, and the pressure will also go down as a result of that. So, sort of an inverse relationship. Volume goes up, pressure goes down, and vice versa. Volume goes down, pressure goes up. Now, what he also found was that if you took measurements of pressure and volume for any gas you like, multiple pressure volume relationships, and if you multiply them together, they will always come out to the same number. So if you have the same gas and you're taking volume sort of relationship readings, they will come out to the same number. And that's what's known as proportionality constant. And because of that, we could kind of get really what Boyle's law is, which is this one here. P1 times V1 is equal to P2 times V2. And once again, this is at constant temperature. And our relationship, pressure goes up, volume goes down, pressure goes down, volume goes up. In this case, the pressures on both sides, this is kind of like a before and after situation. So maybe you change the pressure, you change the volume, you can figure out what happens to the other variable there. The pressure on either side could be whatever unit you want, as long as they are the same unit, so everything cancels out. Same thing here with the volume. The volume could be whatever unit you want on both sides, as long as they are the same, so that they cancel out. So there's no real restriction in this. They have the same. All right, so if we take a look at a graph of this, here we see a small volume and a much larger pressure. And as we give everybody a lot more room to move around in, we see that the pressure drops pretty dramatically there, again, because it's going to slow down on the number of collisions that are occurring. All right, so let's try one here. An inflated balloon has a volume of 0.55 liters. At sea level, 1 atmosphere, goes to 6.5 kilometers, where the pressure is 0.4. What will be the final volume of the balloon? So take a few moments, see what you come up with here. Okay, so let's take a look. A lot of times when you're dealing with gas law problems, it's a really good idea just to pull out the information from the problem, sort of label it, and oftentimes we'll kind of point you to sort of the right gas law to use. Clearly, at this point, we only have one to choose from. That will change very shortly here. But when we look at it, we do have a volume that is 0.55 liters. We have 1 atmosphere, which is a pressure. We have 6.5 kilometers, which is useless in this problem. We have a pressure, which is 0.4 atmospheres, and we are looking for a volume. So just by kind of labeling everything, it should definitely point you to this equation here. In terms of units, we need to check our pressures are both in atmospheres, so that's all good to go. Our volume there's in liters, which means when we solve for it, it will still be liters when it's all said and done. Doesn't matter which ones you call 1 and 2, it doesn't, but usually people go with the first ones in the problem as ones and the second ones as two. As long as you keep the numbers that go together, it's all good. So P1 V1 equals P2 V2. In this case, we're looking for V2. When you have these gas laws and an equal sign, the quick way to rearrange it is when you move it across the equal sign, it ends up in the opposite location, right? So although this is not written as a fraction, both of these guys are up on top, which means we're just going to move that to the bottom on the other side. And that will give us P1 V1 P2 is equal to V2. We're basically dividing, obviously, the P2 to the other side to do that. Putting it in here, we'll go with 1 atmosphere, 0.55 liters divided by 0.4 atmospheres. Atmospheres will cancel, leaves us liters as our units. So 1 times 0.55 divided by 0.4, 1.4 liters in this case will be our new volume. First off, any question on the calculation there? Now we can think about this as Boyle's law, right? So if we think about what is going on, our pressure started at 1, ended at 0.4. So in this case, our pressure went down, which means we should know our volume should go up, right? And we started at 0.55 liters, ended at 1.4. So the volume did go up. So understanding the relationship of what happens with these problems can sometimes perhaps help you figure out if you maybe made a calculation error. So clearly here, if our volume went down, we're going in the wrong direction. Any questions on that there? All right, let's try not that one because it's the one we just did. Let's talk about some more gas laws, and we're going to talk about Charles' law and Gay-Lussac's law. And Charles' law and Gay-Lussac's law looks at really volume and temperature relationship, and it also looks at pressure and temperature relationships. So, for example, Charles' law looks at volume and temperature holding pressure constant. Gay-Lussac's law looks at pressure and temperature holding volume constant. So let's talk about what's just going to kind of logically happen in each of these situations if we do some adjustment. So let's start with Gay-Lussac's law, and we basically have a constant volume in this case of our container, and we have gas molecules in there. And in this case, if I were to increase the temperature, my gas molecules would be moving slower or faster? It would be faster, right? Like you light a match under somebody, right? They move faster. So we increase the temperature. That's going to cause the gas molecules to start to move faster. Because they're moving faster, that means that we should expect a lot more collisions to occur. And what we will actually see here is we would expect the pressure to also go up in this particular case because the volume is fixed. So there's nothing happening with the volume, and they're going to start moving faster, which means we're going to have more collisions and more pressure. Now, opposite of that is if we have our fixed volume here and our gas molecules, and we lower the temperature, our gas molecules are now going to be flying around a lot slower because we lowered the temperature, which means it's going to take, dramatic drawing, a lot longer for these things to start colliding. And that means that we will start to see a lowering of the collisions. And because the collisions are going to start to slow down, we will actually see the pressure start to drop. So because this fixed happens is the temperature determines basically how much collisions we're going to have. So increasing the temperature, more collisions, more pressure, and lowering the temperature, less collisions and lower pressure. Now, if we look at Charles' law situation over here, we have a container with gas molecules in it. And if we increase the temperature in this situation, what's going to happen is, again, our gas molecules are going to be traveling a lot faster, and we would expect a lot more collisions. And that would lead to an increase in pressure. But that's a problem in this situation because we want to hold the pressure constant. So we know that in the situation on the right, when we increase the temperature, we see an increase in pressure because the volume is fixed. What happens in a Charles law situation is, dramatic drawing, the volume will increase in the container. And what happens is, as the volume increases, that's going to allow everybody a lot more room to fly around in. So even though they're moving faster, the Charles law situation is going to adjust to give everybody a lot more space. The result of that is it will be able to keep the number of collisions constant. And because the number of collisions basically remain constant, so does the pressure. So in a Charles law situation, it is actually the volume adjusting that allows for the pressure to remain constant as the temperature changes. Same thing happens here if we decide to lower the temperature. Our volume is going to drop down and come down as well. And the result of that is, as we saw before, as we lower the temperature, our gas molecules are going to be moving slower, which means it would lead to a lower number of collisions. So what happens is the volume just squeezes everybody together. And now, even though they're moving slower, they don't have as far to travel for collisions to occur. And that's able to keep the number of collisions constant as well. And our pressure will remain constant. So that is essentially how Charles' law works. It is that adjustable sort of volume. You could do that with like a movable piston in a container. You could kind of move it up and down, give everybody a little bit more room to move. Rather than what happens in the Gay-Lussac situation where we have a fixed volume that's not going to move, it's rigid, and it's really that temperature now is going to cause a pretty good effect on your pressure, right? Any questions on that there? So when we look at, come back here in just a second, a graph of volume versus temperature using Charles' law relationship, you can make a graph of any gas you would like of volume versus temperature. And if you take the line all the way back to the temperature spot, they will all cross at exactly the same point in terms of the temperature, and that is minus 273.15 degrees Celsius. That number should look familiar. That's the number we used to do what? 273 is how we convert to Kelvin. And Kelvin recognized the nature of this with gases. And if we convert this to Kelvin by adding 273.15, that is 0 Kelvin, which he called absolute zero. So the message here is, when you are dealing with gases and gas laws and you have temperature involved, pretty much it always needs to be in Kelvin, no matter what the situation is. So Kelvin recognized that. He called that absolute zero. And that ultimately means that in all the gas laws that you come across, always, one more time for good measure, always needs to be in Kelvin. That includes problems that commonly mess students up, which is they're given values in degrees Celsius, for example, and they're asked for the answer in degrees Celsius. So they figure, well, obviously I want my answer in degrees Celsius. They gave it to me in Celsius. I could just use Celsius. You cannot. You will get the wrong answer. So you have to convert from Celsius to Kelvin, put it into the gas law, and then after you solve the gas law, convert it from that Kelvin back to Celsius. So always has to be Kelvin in Celsius. Kelvin in Celsius, no, Kelvin in the gas law 100% of the time. So now that we talked about sort of Charles' law and Gay-Lussac's law, let's actually look at what those laws are. Over here on the left is really Charles' law, and this is V1 over T1 is equal to V2 over T2. This is our constant pressure, and as we just talked about, definitely need to be Kelvin there for our temperatures. The volume does not matter, so it could be any unit of volume you like as long as they're the same on both sides. And our Gay-Lussac's law is P1 over T1 is equal to P2 over T2. This is at constant volume. And once again here, our temperature needs to be in Kelvin. And as I mentioned before, the pressure here can be really whatever you like as long as they're the same. So it should be automatic. When you see temperature, you see gas law, you should see Kelvin. Yes, is what you should always see. Any question on those two there? All right, so let's take a look at some here. In an experiment, 452 milliliters of a gas is used in a light bulb, is heated from 22 to 187 at constant pressure. What is the final volume? So take a moment and see what you come up with. Okay, so let's take a look again. I'm just going to pull out the information, see what we got going on. We have a volume that's 452 milliliters. It has a temperature of 22 degrees Celsius, goes to another temperature of 187, and we are looking for a volume. So once again, now we got a few to choose from here. You could hopefully kind of see Charles' law kind of staring at you there if you label it out. And that is going to be our ones. That's going to be our twos. As we just talked about, we do need to make sure that we convert it. And they do want you to use a reminder 273.15 here to do a little conversion. And if we do that there, 22 plus 273.15, we'll go with 295.15 and 273.15 plus 187. We'll go with 460.15 Kelvin. Now that we have that in the right units, V1 over T1 is equal to V2 over T2. In this case here, we are solving for V2. We're going to multiply T2 to the other side, or just frankly move it to the opposite location. Yeah, so that's going to be V1 T2 over T1 is equal to V2. Putting in our numbers in the correct locations, 452 milliliters, 460.15 Kelvin divided by 295.15 Kelvin. Kelvin's going to cancel. That's going to leave us units of milliliters when it's all said and done. 452 times 460 divided by 295.15 looks like 705 here. Milliliters in this case. Any question on that calculation? Once again, here, our temperature in this case went up, which means we know based on Charles' law, our volume should also go up. Started at 452, ended at 705. So again, it did move in the correct way. Yeah. Any questions on that? All right, continuing on our journey here of gas laws. Feel like this is the one we just did, so we'll continue on. Our friend Avogadro, hey, he had a number, but I guess he would like a gas law as well. So when we think about Avogadro, right, we think about our friend the mole. Yeah. So not surprisingly enough, Avogadro's law involves moles. V1 over N1. N is the number of moles equals V2 over N2. This is actually at constant pressure and temperature. And it states that at constant pressure and temperature, the volume of the gas is directly proportional to the number of moles of the gas that are present. So this is Avogadro's law, which obviously you could plug and chug in there, just like all the other ones there, and solve for anything that's missing. A sort of relationship of Avogadro's law that we see is, again, we have 1 mole of gas, we have 1 volume. If we have 2 moles of gases, we have 2 volumes, 3 volumes, 3 moles of gases. A relationship that can be used is actually stoichiometry, a situation where you have all gases and you have constant pressure and temperature. You could actually use Avogadro's law to solve a problem like this. So let's just say, for example, we started with 3 liters of N2, and we want to know how many liters of NH3 would we produce in this case. So in a normal stoichiometry problem, for example, as we'll talk about a little later on in this chapter, we would go through our grams to moles or mole to mole relationship and go into a gas law and sort of solve it. But because this is at constant temperature and pressure, we could actually use Avogadro's law to our advantage. So normally we would go, there is 1 mole of nitrogen is equal to 2 moles of NH3. That's our normal kind of mole to mole relationship. But because of Avogadro's law, we could actually do it with volumes. And we could say for every 1 liter of N2, there are 2 liters of NH3. So just like we could kind of do a mole to mole relationship, we could actually do a volume to volume relationship if they're all gases and it's constant temperature and pressure. So for example, in my example here, we would have 3 liters of N2. We would actually use the Avogadro's relationship here, which means we don't have to worry about grams, moles, or anything like that. And we see that 1 liter of N2 gives us 2 liters of NH3. And in this case, we would actually produce 6 liters of NH3 in this case. So one of the sort of practical aspects of Avogadro's law, in addition to obviously just plugging it in, like I said, and solving for something, is you could actually bypass a lot of work in the stoichiometry problem if it's all gases and it's constant pressure and temperature by just kind of doing a volume to volume relationship rather than sort of a mole to mole relationship. Any questions on that there? We'll talk more about this chapter as well, but that's something to keep in mind. Now, taking all those gas laws together, the ideal gas law, PV equals nRT. It is different than all the other ones for a couple reasons. First off, there is no before and after type of thing. So there's no 2 pressures, there's no 2 volumes, just kind of a one and done situation. The other thing that's different with the ideal gas law is it is the most restrictive in terms of units. So when you use the ideal gas law, your pressure always has to be in atmospheres. Your volume always has to be in liters. N is moles, so it should be in moles. T needs to be in Kelvin. And that is because R is the gas constant. And that is 0.08206 liters times atmosphere, Kelvin times mole. So in order for everything else to properly cancel out with those units, they have to be obviously in the same units. I personally use 0.08206 because that's the number they beat in my head and I can't get it out as much as I try. But a lot of books these days will round this number to 0.0821. But again, I personally will use 0.08206. That you need to know. So you do need to know this. Never given to you. Just assume that you know you have that number available to you. So if you feel like you're missing something, it might be that number. Yeah. And again, it's not typically given to you in problems, just like you should kind of know that you have that. What is an ideal gas? An ideal gas is typically the way gases behave under normal conditions. And there's a couple of things that make something an ideal gas. One thing that makes something an ideal gas is we really don't care about the volume of the gas itself. It is very small compared to the container it's in. So if you think about a lot of problems that we will do, they talk more about the volume of the container the gas is in because we feel it's flying around in that volume of the container and filling it uniformly. The other thing about an ideal gas is you could have multiple gases in the same container and they pretty much won't interact with each other. So there's kind of almost like they're there by themselves. There will be no interaction between those gas molecules and other gas molecules in an ideal situation. Now, a couple other important things with the ideal gas law. One thing is STP. STP stands for standard temperature and pressure. And when they say you want the value at STP, they are actually giving you two values. The pressure at STP is 1 atmosphere, or its equivalent, and the temperature at STP is 273.15 Kelvin. So when you're given in a problem, hey, what is the volume at STP? Those values that you could use to stick into the ideal gas law for temperature and pressure. If the pressure and temperature are not those values, then you are not at STP and you're at some other condition. Now, there's a really nice relationship that happens when you are at STP. And when you're at STP, 1 mole of any gas will equal 22.414 liters. So that allows you in certain cases when you're at STP to not have to use the ideal gas law at all. You could actually just use that as a conversion factor and kind of get to the volume or the moles. But you could only use this if you're at STP. If you are not at STP, you should leave that conversion alone and not use it. The nice thing about the ideal gas law is it's universal, which means if you're at STP, you could use it, just put the numbers into the ideal gas law. If you're not at STP conditions, you could just use it, put the numbers into the ideal gas law. So if you don't even want to worry about that conversion, just roll into the ideal gas law in every situation and you'll be okay. So, but again, you can only use that conversion if it is at STP. That, by the way, is how we get to the gas constant. We put all of our values into the ideal gas law and solve for R. So at STP, we would have 1 atmosphere of pressure. We would have a volume that's 22.414 liters, a 1 mole of gas, and 273.15 Kelvin gives us really our gas constant. So that's sort of how we get to that number that we see there. All right, let's try one here. Calculate the pressure exerted by 1.82 moles of SF6 gas in a steel vessel at 5.43 liters and 69.5 degrees Celsius. Okay, so let's take a look. So once again, we're looking for a pressure here. We do have moles given to us. We do have a volume. And we do have a temperature given to us. So once again, looking through our list here, no 2 pressures, no 2 volumes, no 2 pressures, no 2 volumes. So the ideal gas law here looks like a winner. Remember that not usually given to you in problems, but you always have the R value available to you. So in terms of our volume, we're in liters, so that's good. We're in moles. By the way, a very common thing is you might be given things in grams and has to use the molar mass to go from grams to moles to get it to the moles. Here we do need to do our conversion to Kelvin. So we'll add our 273. So 69.5 plus 273.15. Going to give us 342.65. Now we're going to take our PV equals nRT, in this case here, not really written as a fraction, but we're going to solve for P. So we're going to bring V to the other side and put it on the bottom. nRT divided by V. So putting in our values here, N is 1.82 moles, R 0.08206. Our temperature 342.65. all divided by our volume here of 5.43 liters. Liters will cancel, moles will cancel, Kelvin will cancel. Going to leave us just atmospheres left here in terms of our unit. 1.82 times 0.08206 times 342.65 divided by 5.43. Going to give us a 9.42 atmospheres here as our answer. Any questions on that one? So again, variations on the ideal gas law. A lot of times grams to moles you'll have to do, again, using the molar mass, and also very common milliliters to liters. So 1,000 milliliters is 1 liter, right? So those are two common conversions that you need to do to get everybody into the correct units. Any questions on that there? One last little gas law here to look at. And this is one that involves changes in pressure, volume, and temperature. And if we take the ideal gas law and solve it for R, which is a constant, we could set it equal to each other. And we get what is sometimes referred to as the combined gas law. And the combined gas law is P1 V1 over T1 is equal to P2 V2 over T2. Could also see it like this, where the moles are there, but in a lot of cases, the moles will remain constant as well. So this one that involves the changes in any of these three sort of variables. Now, before we actually do any type of problem with it, if you want to invest your time in learning gas laws, which you need to know all these gas laws, obviously, I would invest my time in the combined gas law and the ideal gas law. The reason that is for this reason. If we take a look, for example, at the combined gas law as P1, V1, and we'll leave the N in there, N1 and T1 is equal to P2, V2, N2, and T2. When we come across a problem, for example, and we have constant moles and temperature, or there's no mention of moles or temperature, all you have to do is scratch those out. And now I have Boyle's law. Now, if you remember this equation, and you come across a problem where there's no mention of pressure or moles, or they're held constant, you scratch out the pressure, scratch out the moles, and there is Charles' law. If you take this equation and you come across a problem where there is no mention of any moles and there's no mention of volume, or they're held constant, you scratch out the moles and the volume on both sides. There's Gay-Lussac's law that we talked about. If you take this guy here and there's no mention of pressure or temperature, you scratch them out. And now you have our friend Avogadro's law, which means if you remember the combined gas law and you remember PV equals nRT, which is your ideal gas law, you pretty much have every gas law that you would need in a problem. So it's a really good one to know, as you could get really all the other gas laws without having to maybe individually remember, all the other gas laws. Any questions on that there? Clearly, we'll use it as a regular gas law like normal, but it's a really good one to remember. Any questions on that? All right, we'll lay it up.